Welcome back to another lesson. It is time to build the neural network that we will use to classify the MNIST dataset. We will once again use the NN module to build our neural network. First, as usual, we define the class that we'll be using to create our neural model instances, and we'll just call it classifier, and it will once again inherit from nn.module. And we need to actually import it first, so what we'll do is back to our top cell, from torch, import nn, back to our bottom cell. Our class will be immediately followed by an init method, def_init. As before, the arguments that go into our def_init function is dictated by the number of hidden layers in our neural network. We will have 2 hidden layers, since I found that to effectively increase the complexity of our model to properly fit the data, and result in a fairly good performance. The first argument, which is always self. The second argument, the number of input nodes, I will call NN. The third argument is the number of nodes in the first hidden layer, which I will call H1. The fourth argument refers to the number of nodes in the second hidden layer, H2. And the fourth argument is the number of nodes in the output layer, which I will call, Dout, and I will call this Dn to stay consistent. And recall the use of super.init for the provision of various methods and attributes. And as we have always done before, we start by initializing the input layer. Self.linear1 is equal to nn.linear, taking in its respective input nodes, dn. And as we are dealing with a fully connected neural network, its output nodes will be simply the number of nodes in the subsequent layer, h1. The second layer of nodes is our first hidden layer, self.linear2, which is going to equal nn.linear, and the number of nodes in the hidden layer is simply whatever nodes that are assigned to it, h1, and its output nodes, which will simply be the number of nodes in the subsequent layer, h2. The third layer of nodes is our second hidden layer, self.linear3, which will equal nn.linear. And the number of nodes in that hidden layer will simply be whatever nodes that are assigned to it, h2. And being that this is the last hidden layer, its output nodes will be the number of nodes in the final output layer, dout. Alright, so we've defined the neural model in our constructor, 1 input layer, 2 hidden layers, and 1 output layer. Now to make a prediction, first what we're going to do is back on top, I am going to import torch.nn.functional as, we're just going to name the alias capital F. Then what we do is, let's get rid of this print statement. It proved our point. All right, so we define our forward function, def forward. And as before, we place the self for the first argument and x. For whatever input we are trying to make a prediction for, whatever input we are trying to feed forward into our neural network, first we will pass this input to the object linear1, self.linear1x. And what I'm going to do is use f.relu this time. We will use the relu function rather than sigmoid. We will cover the relu function in more depth once we get to the next section in convolutional neural networks, but essentially the relu function, just like sigmoid, is an activation function, except relu, through empirical observation, generally performs better in most situations, most notably once we start working with convolutional neural networks. We will go over this in more depth in the next section, but we'll stick with it for now. And the output that we get from this, we're going to assign it to the variable x. And then we take that output and feed it as an input into our second hidden layer. This is a minus f.relu self.linear to x. And similarly, we assign that to our variable x. And now the output that we get from this hidden layer, we feed it into our final layer. X is equal to self.linear3, accepting x as well. However, as we are dealing with a multi-class data set, we will not apply any activation functions here, such that what's returned is whatever value that's outputted by linear3. Why does that matter? Well, by not applying an activation function, what you would get back in the end is the raw output of your network. This is often called the score. This matters when calculating the cross-entropy loss of a multi-class data set, namely nn.cross-entropy loss. You've never seen this before, but essentially, nn.cross-entropy, this loss function is used for multi-class classification. It is a combination of the log softmax and the negative log likelihood loss. We use cross-entropy whenever training a classification problem with n classes. As such, it makes use of log probabilities. So we pass in the raw output rather than the output of a softmax activation function. And this is to ensure that we don't continuously pass in values very close to 0 or very close to 1, since it's hard to precisely represent these values with a float type without encountering approximation flaws. Instead, one uses log probabilities, such that cross-entropy loss just uses nn.log softmax plus nll loss internally. Alright, so overall, just know that as we will be using nn.cross-entropy loss to compute the loss for our multi-class data set, simply make sure that the output that's returned in the end is the raw output, the score, such that no softmax activation function is being applied to it. Anyways, we store the final prediction value into the variable x once again, and we return it. Return x. Alright, having finished setting up our model constructor, what we do now is we will set model is equal to classifier. Nothing new. And according to the initializer, we must set input dimensions, hidden layer dimensions, as well as output dimensions. Firstly, the input dimensions correspond to the pixel intensities of the image that will be fed into our neural network. Since each image is 28 pixels by 28 pixels, 28 pixels traversing the horizontal axis, and 28 pixels traversing the vertical axis, in total this corresponds to 784 pixels that must be fed into the deep neural network. 784 nodes of pixel values in the input layer. So what we do is we set the input size equal to 784. The second and third arguments will correspond to the number of nodes in the first and second hidden layer, respectively. I have tested the following neural network architecture to provide really good results, with 125 nodes in the first hidden layer and 65 nodes in the second hidden layer. The last argument will be the output size. The output size simply corresponds to the number of classes in which each image can be classified in. Since there are 10 classes from 0 to 9, we require 10 output nodes in the output layer. Alright, so what we can do now is output the model, and it displays a model with 784 nodes in the input layer, 125 nodes in the first hidden layer, 65 nodes in the second hidden layer, and rightfully so, 10 output nodes in the final layer. The loss function for our model, the criterion, as you've guessed it, will be nn.cross-entropy loss. This loss function is used for multi-class classification, as opposed to the binary cross-entropy loss that we made use of earlier. We already discussed this, so moving on, we now make use of the familiar optimizer atom by setting optimizer is equal to torch.optim.atom, and we will optimize the model parameters. where the learning rate is equal to 0.01, a relatively low learning rate. As we are dealing with a much more complex data set, that of which is best not handled with an artificial neural network, chances are we'd need a much lower learning rate, and we'll see the effects of that momentarily. Truthfully, it would be much more efficient to be using a convolutional neural network to classify images, but in our case, we will look to tune the learning parameters of our model in an attempt to increase the learning capacity. And having specified the necessary configurations, now it is time to specify the number of epochs in the next cell. We seem to have made an error. Torch.nn has no attributes cross entropy loss, and I think we need to capitalize this. Indeed we do. All right. So what we were doing, specifying the number of epochs, that's what it was. We will set epochs is equal to 12, 10, or 12, whichever one. And following our training process, we will be interested once again in analyzing the losses at every epoch with a plot. So we set up running loss history is equal to an empty list. All right, first we start by iterating through every epoch. And we do this by iterating for e in range of epochs. And for every epoch, we must iterate through every single training batch that's provided to us by the training loader. So, for, and each training batch will contain 100 images as well as 100 labels in train loader. And I think I called it training loader, not train loader. Let me just make sure, and indeed I did. As we iterate through our batches of images, we must flatten them. We must reshape them with the familiar view method. And you know what? Instead of calling these images, for consistency, I'm going to call them inputs. And then we write inputs is equal to inputs.view. Remember, we are reshaping them and recalling the shape that we printed out earlier. Noting that the shape of each image tensor is 1 by 28 by 28, 784 pixels in total. However, due to the structure of our neural network, our input values are going to be multiplied by the weight matrix connecting our input layer to the first hidden layer. To conduct this matrix multiplication, we must make our images one-dimensional. We cannot pass the tensor in the way that it's currently shaped. That is, instead of each image being 28 rows by 28 columns, we must flatten it into a single row of 784 row pixels. We leave the color channel in index 0 as is, so we don't change that. We leave that as inputs.shape0. And in the index 1, that will contain the number of pixels. By putting -1, it will simply infer the total value of our second index. This is the inputs, or these are the inputs, I guess, that will be fed into our model. And from these inputs, we obtain outputs. Outputs is equal to model inputs, calling upon our forward function. Recall that the forward function will end up giving us the raw output, the final score, rather than a final probability, to which log softmax is then applied. We use this to calculate the total categorical cross-entropy loss. And once again, the output is ultimately compared with the actual labels. We're comparing the outputs and the labels, and we determine the error based on the cross-entropy criterion. Nothing new. Before performing any part of a training pass, we must set optimizer.0grad. All right, so we've determined the loss by comparing the outputs to the actual labels. What we can do now is call the usual functions loss.backward as well as optimizer.step. And now to keep track of the losses at every epoch, before every epoch iteration, what we're going to do is we're going to set a variable running loss is equal to 0, 0.0. And for every loss that's computed per batch, we must add them all up for every single batch in order to then compute the final loss at every epoch. So what we do is we set a running loss plus equal loss.item, the current loss at the batch iteration. And then what we're going to do is append this accumulated loss for the entire epoch into our losses list. However, before we do that, after the for loop, we can put an else statement. So when this for loop is finished, such that we've iterated through every single batch of images, the else statement then gets called. In that else statement, we want to print the accumulated loss that was computed for the entire dataset at that specific epoch. So we set epoch loss is equal to the running loss divided by, and since the running loss was accumulated for every single batch iteration, we divide by the number of batches, length training loader, in order to get the average loss at the epoch. All right, and now since we want to keep track of the loss at every single epoch, what we're going to do is append every epoch loss into our running loss history list. So we set running loss history dot append epoch loss. In doing so, we can observe the decrease in loss at every single epoch by plotting this onto a graph. All right, and finally, what we're going to do is we're going to print training loss is going to equal a placeholder, and we're going to format our placeholder into a floating point number with 4 decimal places. That is .4f. And into this placeholder, we will format it. Format to replace it with the epoch loss. As we are also interested in the accuracy of our network, all the same, we will set running corrects history also equal to an empty list, which will store the accuracy at every epoch. At first, when the epoch first starts, we set running corrects is equal to 0.0, and what we want to do is compare the predictions made by the model for each training image to the actual labels of the images to see how many of them it gets correct within an epoch. How do we do that? Well, we already set output is equal to model images, and what that will contain is a bunch of score values. And it follows that the class which contains the highest score, by passing it into the softmax function, it will then have the highest probability, meaning the highest score is the class prediction that it makes. Every image that's inside of inputs, recall inputs is just a batch of images. Every image in this batch of images will then yield a bunch of scores. For each image, we want to take the maximum score value, torch.max. And we want the maximum value for each output in outputs. And we'll leave this argument as 1. In such a case, a tuple is returned. The first value it gives back is the actual top value, the actual top score, the maximum score that was made by the model for every single image within this batch of images that was iterated through. And what we want to do is compare the predictions made by the model for each image to the actual labels of the images to see how many of them it got correct. So we're not too interested in this first tuple value. And now the second value will correspond to the top predictions made by the image, which I will call preds. Ultimately, it's going to return the index of the maximum value for that image. Since each image output will be a collection of values with indices ranging from 0 to 9, such that the MNIST data class contains classes from 0 to 9, it follows that the index where the maximum value occurs corresponds to the prediction made by the model. Essentially, this variable will contain the top class prediction for each image from our batch of images. And we want to compare all of these predictions made by the model to the actual labels of the images to see how many of them it got correct. So what we do is we do this comparison with the equal operator. Preds is equal to labels.data. And what that's going to do is for every single element of both tensors, it will compare the prediction of the class made by the model for each image with the actual label of each image, its actual class. If the comparison at some element does match, if the model made the correct prediction, at that element it will place a value of 1. So for every prediction that it gets right, we want to take the sum of that. And we do that with torch.sum. And that will give us back the number of correct predictions for a single batch of images. And as we want the number of correct predictions for every single batch of images, we increment plus equal the number of correct predictions for every iteration into running corrects. Let's place that under running loss, like so. We then define epoch accuracy in much the same way as epoch loss, such that it's equal to, well, epoch accuracy is equal to running corrects dot float divided by the length of the training loader once again. Basically, once we loop through the entire data set, by dividing the number of classes it predicted correctly by the total number of batches, that should give us the average accuracy at that epoch. And so what we're going to do is add another placeholder inside of our print statement, the same placeholder as before, and this will contain the accuracy. Simple enough. Dot format epoch accuracy.item. All right, having done so, it is time to train our model. All right, and something tells me that we messed up when declaring our classifier, and I seem to have forgotten an indentation right here. That's not very good, and what I'm going to do is actually fix the indentation here as well. And overall, we should be good to go now. All right, I'm just going to actually reset the runtime and rerun all the cells, see what happens. This might take a while, so I will see you guys in a bit. All right, and having completed the training process, one could conclude that it seems the performance saturated at 95% and the loss couldn't go as low as 0.15, 0.14. One can simply analyze the following data, but to make conclusions on the training loss and performance, and for visualization purposes, it would be better to actually see what's going on with a bunch of plots. So we set plt.plot, and we will first plot the running loss history. We will label it as training loss per epoch. We will not need anything else. Let's just plot the following. All right, and there is one thing we can notice right away. There are many reasons for why we couldn't get the loss to fully minimize. Plotting the following loss, although it seems to minimize as the epochs progress to a final value of 0.15, there is one problem, and you can clearly see that the loss kind of fluctuates as the epochs progress. Recall the concept of gradient descent, which gradually adjusts the parameters of your model in the direction of the least error, descending with the gradient. The steps that it takes to arrive to optimal parameters is dictated by the learning rate. If the learning rate is too high, the steps it takes will be too large, such that the parameters will in a way flip-flop back and forth between points, overshooting the minima, and thus leading to divergent losses. Generally speaking, decreasing the learning rate allows the model to better zero in on a solution for the parameters. Since we're dealing with a more complex data set, it is imperative that we ensure an efficient training process, which is why we will decrease the learning rate by a factor of 0.01. In this specific case, given the other hyperparameters that we specified and the data that we're dealing with, it should ensure a smoother learning process, as divergent losses are an indication that one should decrease the learning rate in one of two general scenarios: if you see that the learning is very slow, or if the loss gets stuck in a local minima. A loss function can have many minima with different loss values. A low learning rate can cause for the loss value to get stuck in such a minima, whereas a higher learning rate's inherent divergent behavior in that case would allow the parameters of the model to escape these local minimas. As our goal is generally to reach the absolute minimum of the loss function, to minimize the loss as much as we can while still generalizing to new data, an indication of getting stuck in a local minima can be observed when the use of a low learning rate results in a loss that stops decreasing at a relatively high value. In such a case, although it might seem counterintuitive, then increasing the learning rate would result in a better solution. There's this consistent trade-off that one should always be mindful of. There are many ways of finding an optimal learning rate, some of them quite systematic, which you can find through papers online. The most general one is to try and start with a high learning rate and then adjust it based on empirical results. Is the learning too slow? Is the loss too high? Is the loss diverging? Is there overfitting? And adjust the model's capacity accordingly. And the reason that I stress this is because the learning rate is quite an important hyperparameter to tune. It can make the difference between a good model that yields accurate and generalized results as opposed to one that doesn't learn well. In our case, we see quite a bit of divergence in the loss, and now we adjust it accordingly. One can also claim that due to the complexity of the data that we're dealing with, in comparison to the two-dimensional coordinates that we dealt with earlier, and for our purposes, this learning rate should serve us well. So what we're going to do is retrain our model. I will re-instantiate it and retrain it accordingly. All right, this should take quite a while, being that we increased the learning rate to such a low value. So what I'm going to do is actually pause this recording and see you in quite a bit. All right, we see a much smoother training process. It seems that as the epochs progress, the loss continuously decreases. It's not flip-flopping back and forth. Had we specified more epochs, it seems that the loss would have still continued to decrease. So we see a much smoother learning process with a fairly reasonable accuracy. If we plot the loss, clearly a lot smoother. We can now plot the accuracy at every epoch with plt.plot running correct history with label training accuracy. In doing so, I may have messed something up. plt.plot running correct history. Oh, forgot to specify the label keyword. And it seems that we may have messed something up in our code from earlier. One thing I want to point out is this print statement is not consistent with what we're seeing. We should specify that this second placeholder denotes the accuracy. And the reason the accuracy does not show is simply because we forgot to actually append our epoch accuracy into running correct history, so we append it. .append epoch accuracy. And what we're going to do is actually specify a higher number of epochs to allow the model for a chance to better hone in on its optimal parameters. All right, reinstantiating the class and restarting the training process, we should see better results. I'll see you in a bit. All right, as we predicted, a learning rate of 0.0001 yields a much smaller error, and it looks like it could have still decreased even more, but regardless of that, we replot the running loss history. It's a consistent decrease in loss, and we replot running correct history, and it's also a consistent increase in performance. This is really good. We see a reasonable accuracy in our model. However, this begs the question. Our model is doing pretty well on training data at the moment. However, is our model able to generalize itself to new data that it hasn't seen before? Is our model overfitting? Or is it able to take what it has learned on the training data and apply it to new data? We will figure this out by validating our model, and this will be done in the next lesson. See you there, guys.